So far we have seen how to find Fourier series expansion of continuous periodic signals. But now we will see how to extend this idea to find continuous aperiodic functions. We will do so by making the period of the function to approach infinity. Now let me first draw a periodic signal. Now this function is t0 periodic, and t0 is equal to 4 times t1. And Fourier series expansion of this function would look like this. That's a sinc function, and its components are one here, one in this point, one at that point. We have zeros at these points and one at this point. It goes on like that. But let's see what happens if we move recurring parts of this periodic function away from each other. Now we will move them away from each other. And this time I will make t0, the periodicity of this function, is equal to 8 times t1, which is double the frequency of what we had here. Now this point is t0, which is equal to 8 times t1. As you can see, we have moved each part of this periodic function away from each other. We have extended this space. But let's see what happens to Fourier series expansion of this function. Now we can see that between this component and the zeroth component, now we have 1, 2, 3, and 4 components. But before we had only 1 and 2 components. Therefore, when we double the period, its Fourier series expansion gets narrower. So that means if we push components of this periodic signal to infinity, where t0 is going to infinity, the Fourier series expansion of that would become a continuous function this time. Why? Because each component coefficient will get so close to each other that that will turn into a continuous function. So as a summary, we can say that continuous periodic functions will give us discrete coefficients. Continuous aperiodic functions will give us a continuous aperiodic function. This part is Fourier domain, this part is time domain. If you look at this Fourier domain, those are our CNs, or Fourier series coefficients. We have already seen how to find them. Cn is equal to 1 over t times integral over a period of f of t times e to minus j 2 pi over capital T times n times t. Now if you look at this formula, we have pushed this period t to infinity. And we have seen that as we push this period to infinity, coefficients gets closer to each other. So this n gets closer to 0. Therefore, intuitively, we can say that n over t approaches to a continuous value mu. So now we are ready to derive continuous Fourier transform instead of Cn's. So now instead of Cn, we have a continuous function. So let's call this transformation Fourier transformation of f of t, which will give us a continuous function in Fourier domain, is equal to, in this case, we do not have 1 over t. Again, we have an integral, but now since we have pushed each recurrent component of this periodic function to infinity, we should take this integral over infinity. F of t times e to minus j 2 pi, this instead of n over t, now we have mu times t dt. And this is our formula for Fourier transformation, not the Fourier series expansion. We can take Fourier transform of any continuous function. It doesn't have to be periodic. And what's the inverse Fourier transform? And this is inverse of Fourier transform of ft, which gives us ft again, and this is equal to, now I will make a change to the top part of the equation and call that part f mu of t. So this integration becomes from minus infinity to plus infinity. This should be f mu, f of mu. Here f of mu, which is Fourier transform of ft, times e to plus j 2 pi mu times t. But this time we are taking integral on mu. And this is Fourier transform pair for continuous time signals.